I want you to imagine taking all that excess carbon dioxide that's currently heating up our planet, just pulling it straight out of the air and literally recycling it into valuable industrial chemicals.
Yeah, like plastics, textiles, solvents, all of that.
Right. And now imagine doing all of this just by feeding electricity and carbon dioxide to a vat of microscopic bacteria.
Which, I mean, it sounds like pure science fiction.
It really does, or at least something that's, a few decades away. But making that sci-fi vision a reality basically comes down to one massive microscopic bottleneck. So today we are doing a deep dive into a recent breakthrough from the Chemical Engineering Journal to find out how a microscopic spiky metal flower might actually be the key to saving the planet.
It is honestly a phenomenal piece of engineering. So we're talking about microbial electrosynthesis, or MES.
MES, okay.
Yeah. The premise here is that instead of treating carbon dioxide as a waste product that we have to bury underground, we treat it as a raw material. We close the loop.
Which makes sense.
Right. But to do that, you run straight into the fundamental laws of thermodynamics.
Yeah.
Because carbon dioxide is incredibly stable. It's essentially the chemical ash that's left over after combustion.
It's already burned up.
Exactly. So getting it to react and form complex multi-carbon molecules usually requires a massive amount of brute force.
And when you say brute force, you mean like the traditional methods of carbon capture and utilization, the thermochemical approaches.
Essentially, yes. In traditional industry, if you want to force CO2 to become something useful, you're typically heating it to hundreds of degrees Celsius, putting it under intense pressure, and using insanely expensive noble metals.
Stuff like platinum.
Platinum, palladium, they act as catalysts. But it's an energy-intensive fight against physics. And even with all that heat and pressure, those processes really struggle to selectively build complex compounds.
Just end up with a mess.
Yeah, they often yield a messy soup of basic molecules.
Which is why the biological approach, this microbial electrosynthesis we're talking about, is so attractive. Because we step away from the brute force and just let nature do the heavy lifting.
Precisely. In MES, the scientists are using electroactive bacteria as a biocatalyst.
And the beauty of a living biological catalyst is that it operates at a perfectly comfortable room temperature. Plus, it's self-healing.
Right. If an enzyme breaks down, the bacteria just grow a new one.
That's wild. And they take the CO2 and selectively convert it into a specific value-added chemical like acetate with a precision that human chemistry just totally struggles to match.
Because bacteria has spent billions of years evolving enzymes specifically designed to manipulate carbon. I mean, we're simply hijacking that evolutionary precision.
It makes me think of a microscopic futuristic brewery. Like, instead of feeding yeast a bunch of sugar to brew beer, we're feeding electroactive bacteria a steady diet of electricity and CO2 to brew industrial chemicals.
I actually love that comparison because it highlights the core mechanical challenge here.
Oh, how so?
Well, just like a traditional brewery needs water and grain pumped into the vats continuously, your futuristic brewery needs a constant supply of raw materials too. To biologically reduce carbon dioxide into acetate, the bacteria require a steady stream of protons and electrons.
That's their fuel.
That is their fuel.
Yeah.
And you can't just buy a tank of protons and electrons. You have to generate them on-site, continuously, within the reactor itself.
Right. And generating that fuel requires an electrical power source to drive a chemical reaction, which I'm assuming introduces a massive hidden inefficiency into the whole system.
Oh, massive.
It's like the actual mechanics of this brewery. Because of the biological side, the microbes hanging out in the cathode chamber works beautifully at room temperature, so the real problem shifts to the chemical side of the tank, specifically the anode.
Yes, the anode. It's the piece of hardware responsible for actually generating the electrons to feed those bacteria.
So what exactly is the anode doing in there?
Its job is to drive what chemists call the oxygen evolution reaction, or OER. In plain English, it's splitting water.
Okay, splitting water.
Right. It takes two liquid water molecules and literally rips them apart to generate one molecule of oxygen gas, 4 protons, and 4 electrons.
Yeah.
Those protons and electrons then travel over to the biological side, where the bacteria are waiting to consume them.
But splitting water is notoriously difficult, isn't it? Because water is another one of those very stable molecules. It doesn't want to be ripped apart.
It is a kinetic nightmare.
Oh.
Oxygen holds onto its hydrogen atoms tenaciously.
It really wants them.
Yeah. To break those bonds, you have to rip 4 electrons away at essentially the exact same time. The thermodynamic minimum energy required to make that happen is
1.23. That doesn't sound too bad.
Well, that's just the theoretical floor in a perfect universe. In the real world, because of the physical resistance of the materials and the sluggishness of the chemical reaction, current MES systems often have to pump in anywhere from 2.5 to over 5 volts just to force the reaction to occur.
Wait, so if you need 5 volts of input to achieve 1.23 volts of actual chemical work, the math on that is brutal. You are wasting the vast majority of the electricity you plug into the system.
The paper explicitly points out that 70 to 80% of the input energy in these biological systems is totally wasted. It's lost as heat or simply consumed trying to overcome the kinetic barriers of splitting water. In chemistry, we call this energy tax the overpotential. It's the extra juice you have to squeeze into this system just to get the reaction moving at a useful speed.
An 80% energy tax makes the whole idea of green carbon capture seem, well, a lot less green, especially if that electricity is coming from a fossil fuel grid. So how do chemists usually avoid paying that tax? I assume the standard move is to just throw expensive metals at the problem.
That is the traditional playbook, yeah. Use noble metals like iridium or ruthenium to act as catalysts. They make the water splitting much easier, lowering the overpotential.
But they cost a fortune.
Exactly. Alternatively, if you want to use cheap, earth-abundant metals,
Right.
like plain iron or nickel,
Yeah.
you have to alter the water itself. You make the water highly acidic or highly alkaline.
Oh, I see.
Because in those extreme pH environments, cheap metals can suddenly split water quite efficiently.
Okay, wait. So we need a cheap metal that performs like an expensive one, but we are running a biological brewery. If we dump a bunch of acid into the tank to make the cheap metal work better, wouldn't that instantly melt our biological workforce on the other side?
It absolutely would.
Yeah.
And that is the ultimate paradox here. Researchers call it the oxygen dilemma.
The oxygen dilemma.
Yeah. The electroactive bacteria need a comfortable, completely neutral pH environment, somewhere around 7.1 to 7.6, to survive and actually produce acetate. They can't survive in a vat of acid or industrial bleach.
Obviously.
But at a neutral pH, the concentration of free protons floating around in the water is incredibly low.
So the cheap metals essentially have nothing to work with. They just sit there, or worse, they corrode and fall apart because they don't have the extreme pH to facilitate the reaction.
That is the wall the industry hit. We desperately need a catalyst made of cheap, non-noble transition metals that can split water highly efficiently. But it has to do it in neutral pH conditions to keep the bacteria alive.
Which sounds impossible.
It's tough. We needed a structural and chemical breakthrough that forces everyday metals to behave in extraordinary ways.
Which brings us to the actual innovation in this chemical engineering journal paper. Because the researchers couldn't change the laws of biology, so they had to completely reinvent the physical geometry of the metal.
Yes, they forged a completely new catalyst.
They abbreviate it as nicopene. Let's break down what that actually is, because the sheer physical structure of this thing sounds bizarre.
It is pretty amazing. The composition is a nickel-cobalt phosphate, which they layered onto a substrate of highly porous nickel foam.
Okay, nickel foam.
Yeah, they used a modified hydrothermal synthesis process. Essentially, they put the materials in a high-pressure, high-temperature environment, literally cooking it, which caused nickel atoms to leach directly out of the foam substrate and integrate with the cobalt and the phosphate in a very specific pattern.
And the physical shape that grew out of that process is wild. I mean, when you look at the images they took using a scanning electron microscope, it looks nothing like a flat piece of metal.
No, not at all.
It looks like a microscopic, spiky, blooming flower, or like a metallic sea urchin. It has these sharp individual spikes that are about 5 micrometers wide, all radiating outward from a central core.
Right. And for context, a human hair is roughly 100 micrometers thick.
Okay.
So we are talking about a dense forest of incredibly tiny metallic needles.
And that spiky geometry serves a vital electrochemical purpose, right?
Absolutely. In catalysis, the name of the game is surface area. The reaction only happens where the water physically touches the metal. So a flat sheet of nickel only has so many atomic parking spaces for water molecules to dock and get split apart.
So by growing a microscopic sea urchin, you are exponentially increasing the surface area. You're basically folding thousands of new parking spaces into the exact same microscopic footprint.
Exactly. And to prove just how much space they created, the researchers measured what's called the double-layer capacitance.
What's that?
Think of it as measuring how much static electrical charge the surface of the material can hold. It correlates perfectly with how much microscopic surface area is actually touching the liquid.
Okay, got it.
The nicopene flower achieved a capacitance of 2.03 millifarads per square centimeter.
Is that a lot? It sounds like a small number to a layperson.
In the context of these electrodes, it's massive.
Yeah.
It is vastly higher than a standard piece of bare nickel, and it dwarfs the standard graphite felt that many labs use.
Wow.
The spiky architecture provides a huge playground for the water molecules to interact with the active sites. But, the physical shape is only half the story. The chemical interaction between those metals is what actually drops the energy tax.
Because having more parking spaces doesn't help if the water molecules still refuse to split apart once they park. How do we actually know these metals are doing something different on an atomic level? You can't exactly watch individual atoms trade electrons through a normal microscope.
No, you can't. So the researchers used X-ray photoelectron spectroscopy, or XPS.
XPS.
Yeah, it's a technique where you bombard the material with X-rays and measure the kinetic energy of the electrons that get knocked off. It tells you exactly how tightly the atoms are holding on to their electrons.
Oh, that's clever.
And the data here was fascinating. They found that the binding energies for the cobalt and the nickel had shifted by about 1.4 electron volts compared to when those metals are alone.
Okay, so the metals are chemically interacting. What does a shift of 1.4 electron volt actually translate to in terms of splitting water?
It means that within this spiky structure, electrons are being naturally pulled from the cobalt over to the nickel. The cobalt becomes slightly more positive, and the nickel becomes slightly more negative.
They form a localized internal electric field.
Exactly. So when a water molecule docks in that parking space, it gets caught in an electromagnetic tug of war. The customized electron sharing between the nickel and cobalt physically strains the bonds of the water molecule, making it much, much easier to rip the oxygen and hydrogen apart.
And we haven't even mentioned the phosphate group yet. The acronym is NicoPi, with the pi standing for inorganic phosphate. What's its job in this tug of war?
The phosphate acts as the catalyst's internal repair mechanism. It facilitates what is known as proton-coupled electron transfer.
Which means what, exactly?
Well, in that neutral pH water where free protons are incredibly scarce, the phosphate groups are exceptionally good at grabbing whatever protons are available and shuttling them away from the active site.
Okay, that's incredibly efficient.
Furthermore, in a neutral environment, if the sharp metallic spikes start to degrade under the violent electrical stress of splitting water, the phosphate ions dynamically rebuild the surface. It is literally a self-healing metal.
Let's take a step back and look at what we actually have here. We started with the need to split water to feed bacteria, but we were blocked because cheap metals don't work in the neutral water the bacteria require.
Right.
Now, researchers have cooked up a microscopic, electron-sharing, self-healing, spiky metal flower that solves the chemistry without poisoning the biology. But theory and half-cell lab tests are one thing. Does this actually work inside a flowing, messy biological reactor?
That is the big question. Integrating a novel material into a living biological system is the ultimate crucible. You have to prove that this anode can maintain its efficiency while sharing a tank with organic compounds, varying flows, and, living organisms.
And the researchers did just that. They built a dual-chamber microbial electrosynthesis reactor, dropped their spiky metal flower into the anode side, and let it run continuously for 20
And the results were stunning. Let's look at the real-world reduction in that energy tax. We discussed how traditional setups require massive overpotentials to drive the reaction.
Right.
With the Nicopani anode in place, the overpotential plummeted to just 347 millivolts to achieve a benchmark industrial current density of 10 milliamps per square centimeter.
Dropping from volts of wasted energy down to roughly a third of a volt is a monumental leap in thermodynamic efficiency.
It stabilizes the entire system. Because the water splitting was happening so smoothly on the chemical side, the total voltage required to run the entire reactor, both the anode and the cathode, leveled out at just 1.
That is fantastic for the power bill. But what about our futuristic brewery's output? Did the electroactive bacteria actually thrive and produce anything useful over those 3.5 weeks?
Oh, the biological performance was superb.
Sure.
The bacteria continuously converted the injected carbon dioxide, and the system accumulated 14.5 millimolars of acetate.
Let's pause on that number. To a general audience, is that enough acetate to fill a swimming pool, or are we still talking about droplets in a beaker? Does this prove the tech is ready for an industrial plant?
We are definitely still at the laboratory scale. 14.5 millimolars in a small reactor isn't going to replace a massive petrochemical refinery tomorrow.
Right.
But the sheer volume isn't what makes that number so important. It's the purity. Acetate was the only carboxylic acid produced. There was zero methanogenesis.
Meaning the system didn't waste any energy accidentally producing methane gas?
Exactly. It was a highly selective, incredibly clean biological conversion. That purity is exactly what you want to see before you attempt to scale a technology up to commercial vats.
And the ultimate metric tying this all together, the number that determines whether this climate tech actually makes economic sense, is the overall electrical energy efficiency. How much of the electrical energy pumped into the system successfully stored itself in the chemical bonds of that acetate?
The spiky flower system achieved a staggering 75.8% electrical energy efficiency.
Which is incredible when you realize that just a few minutes ago we were talking about 80% of the energy being wasted.
It's a total flip.
To give some context to how big of a leap that is, the researchers ran control tests. When they powered the exact same bacteria with a bare nickel anode, the system only hit 69.5% efficiency. And when they used standard graphite felt, which is very common in these labs, the efficiency plummeted to an abysmal...
Over half the power was wasted with graphite. The microscopic architecture of the spiky flower directly and immediately translated into a massive system-wide efficiency boost.
But I want to push back on this a little bit because there was a very revealing caveat buried in the testing data. The researchers decided to run a specific test to see what would happen if they stopped managing the surrounding environment.
Yes, the failure test.
Yeah, they ran the reactor without actively controlling the pH on the chemical side, and things went catastrophically wrong.
They really did. You have to remember that splitting water naturally generates an excess of protons. If you do not actively buffer or manage the water, those protons accumulate rapidly.
And the water gets acidic.
Extremely acidic. Within just a few days of turning off the pH control, the water in the anode chamber plummeted from a comfortable neutral 7.5 down to an incredibly harsh, acidic...
And the system practically tore itself apart. The cell voltage violently spiked up to over 11 volts, the current flatlined, and that beautiful, highly engineered spiky metal catalyst literally corroded away.
Wait, so if a chemical pump fails, or a valve sticks in a real-world plant and the pH drops, this miracle metal just eats itself alive? Does that extreme fragility make this technology practically useless for a massive, messy industrial operation where things go wrong all the time?
It is a totally valid concern, but it doesn't render the technology useless. It simply defines the engineering requirements. It underscores that microbial electrosynthesis is a deeply coupled bioelectrochemical system.
It's a package deal. Exactly. You are entirely correct that you cannot just install this metal flower in a tank, walk away, and expect it to run forever. It's like buying a high-performance, precision-tuned sports car. You cannot drive a sports car through a muddy ditch and be surprised when the suspension shatters.
You have to pave the roads first. The environment has to support the hardware.
Precisely. The macro-engineering of the facility, maintaining that delicate 7.5 pH balance through automated buffers, is just as critical as the nano-engineering of the catalyst itself.
Which is standard practice anyway, right?
Oh, absolutely. Industrial process control handles precise pH buffering in massive wastewater treatment plants and commercial breweries every single day. The capability exists. The key takeaway from the failure test is that the biology and the chemistry are inextricably linked.
Right.
When the pH dropped and the anode dissolved, it didn't just ruin the metal. The voltage instability transferred across the tank, disrupting the steady flow of electrons to the bacteria. The microbes essentially starved, and the protein levels in their biofilms crashed.
So it's a symbiotic machine. The bacteria need the spiky flower to efficiently rip apart water so they can eat, and the spiky flower needs the environment to be carefully managed so it doesn't dissolve.
You nailed it.
But when those conditions were met during the 24-day run, the stability was rock solid. The catalyst maintained its low energy tax for weeks without any sign of degradation.
That sustained stability proves the fundamental viability of the mechanism. The self-healing nature of the phosphate groups, combined with the electron sharing of the nickel and cobalt, creates a remarkably resilient system as long as it operates within its design parameters.
So what does this actually mean for you, the listener? Why does a microscopic sea urchin made of cheap metal matter to the future of our planet? Let's trace the journey we've been on. We started with the global necessity to capture excess CO2 and turn it into something useful rather than just burying it.
A huge challenge.
We looked at microbial electrosynthesis, a brilliant, elegant biological solution that uses bacteria as a room temperature brewery. But we uncovered a massive hidden bottleneck, the sheer amount of wasted power required to split water to feed those bacteria.
And the solution to that oxygen dilemma didn't come from genetically modifying the bacteria to work harder or from mining rare exorbitant metals from the earth. The breakthrough came from completely rethinking the physical geometry and atomic synergy of cheap, everyday transition metals.
By using nickel, cobalt, and phosphate to grow a microscopic, spiky architecture, researchers dramatically increased the surface area, altered how the metals share electrons, and created an electromagnetic tug-of-war that rips water molecules apart with unprecedented ease.
It's brilliant.
They took a process that routinely wastes up to 80% of its energy and flipped the script, achieving a system-wide electrical efficiency of nearly...
It is a masterclass in interdisciplinary science. The biological promise of carbon capture was entirely bottlenecked by a material science problem. Solving climate challenges requires us to look across scientific boundaries. We proved that sustainable carbon utilization doesn't require platinum. It just requires a brilliant, microscopic architecture.
So, the next time you are reading a newsfeed and you see a flashy headline about genetically engineered bacteria that eat greenhouse gases, you will know the deeper story. You will know that the real hero making that futuristic biological brewery commercially viable might just be the unglamorous, highly engineered piece of spiky metal sitting in the opposite side of the tank, quietly ripping water apart.
It's a profound reminder that the solutions to global atmosphere scale problems are often found at scales we cannot even see with the naked eye.
Which leaves us with a final thought for you to ponder. If simply changing the microscopic geometry of cheap, everyday metals, forcing nickel and cobalt to grow into a flower-like structure, can alter how they share electrons and unlock such massive system-wide energy savings, what other massive global inefficiencies are currently hiding in plain sight, just waiting for the right spiky flower to unlock their potential?